Okay, I want to start this lesson on primes and composites, which is section 4.2, what we were moving on, not by talking about the quick thought, but I wanted to actually go into um, the material. So let's let's start with a simple question. I want you to represent 12 using unit squares. And so you don't have to actually um, pull out some physical squares. I want you to just try drawing a little sketch of how you would represent it and consider what you could do. So I'm going to pause the video and draw mine out, and let's see if mine match what you have. All right, looking at my 3 different representations, which you only needed one, um, hopefully you had something that looks somewhat like one of these. But are these the only representations I can do? We've talked about multiplication and creating visuals for multiplying numbers. And so what I have here is a 12 times 1, 6 times 2, and 4 times 3. Can I also draw this as 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12? I think that's 12. Whether or not it's neat enough, that's a whole nother question. So anyway, can I draw this like that as a 1 times 12? And is that the same representation? Is it still the same as what I have down here? Or is it a new value? Is it a new piece of information to look at? Then I could also do 1, 2, 3, 4, 5, 6. 2 times 6, like this. And again, is this the same rectangle? You know, that's a little bit more up for debate. That's a little bit more open-ended and how you want to interpret it. But the fact of the matter remains, my rectangle has only shifted. It isn't a new rectangle. But my number pairs are the same as well. So I have represented 12 using 1 times 12, 2 times 6, and 3 times 4. I have broken this down into its divisors. These are all called divisors. So 12 can clearly be broken down into at least, depending on the way you look at it, 3 rectangles of varying dimension. But let's think about a different rectangle. Let's see if I can do this. Yes. Let's think about the rectangle for 7. I know I can do this one. A 1 by 7. And I can sort of do this one. This is a 1 by 7 again. My rectangle hasn't actually changed though. And if I looked at the number pair, I have 1 times 7. And is it useful for me to write down 7 times 1 again? Because I don't really think so. I can only represent it using one pair. And this actually leads us into today's topic, primes and composites. So a prime number is a number that, only has divisors 1 and itself. Whereas a composite, let me pause the video for a second. Sorry, I wanted to just write out the definition real quick. So a composite definition is that it has positive factors other than 1 and itself. And that seems like a really basic definition, but they don't rely on each other. They don't use prime or composite in each other's definitions. And so it's as straightforward as we can possibly get. And so we know that 7, 1 and 7 is prime, whereas 12, 1 and 12, 2 and 6, and then 3 and 4 this row here was all I needed to know that this was a composite value, whereas this is a prime. And, you know, we make a big deal of prime numbers. We really highlight so much information about them, and there's all these theorems and research into what prime numbers are and blah, blah, blah. But what's important for us to note is that they are kind of indistinguishable. They're hard to see just because they don't have set patterns in the way that they function. And so what's useful for people is to use what we learned last time, the rules of divisibility. And my online students, if you are watching this, I know that I have not uploaded my notes for that, but the notes that we took in class were kind of difficult to read simply because the computer in that classroom, unfortunately, it wasn't working on Wednesday before we left, and so I had to write on the board. So I have a bunch of pictures, and I will put those together, but they're not going to be that great. They're basically just listing the rules. So if you do have questions, that is definitely a topic that I highly recommend you take a look at the textbook and you ask me if you have any questions. We didn't do anything special. We just, well, I'll show you what we did in a little bit because it's part of this lesson too. So 1564, I'm just going to, I'm sorry, so I have four numbers here, and I want to know, are they prime or are they composite? And so I'm just going to go through and tell you, well, I'm going to figure it out, if each number has something else besides 1, because I know we have 1 in 1564. But I want to know, are there any other divisors, any other factors? And looking at this, I already know, based on my divisibility rules, that 2 divides 1564. For anybody who does not remember that notation, this is read as 2 divides 1564. That's what this is, and this bar shows that it divides it. Okay? It's notation to show that 2 times some number equals 1564. Some whole number. Anyway, so 2 divides 1564. That means that this is a composite. 2781, well, it's not even, so 2 doesn't work. Let's see, let's try 3. 2 plus 7 plus 8 plus 1. That's 9 plus 8 is 17 plus 1 is 18. So 3 divides 18. And so that means I'm trying the rule of 3 right here, just for anybody who doesn't know. You might want to look up the rule if you don't remember it. 3 divides 18, so that means that 3 divides 2781. For anyone who doesn't remember and hasn't looked up the rule yet, this is simply to say you take all the digits and you add them up, and if 3 can divide that sum, then 3 divides the regular number. So this is also composite. Here, 1001, it's not even, so 2 does not work. And 1 plus 0 plus 0 plus 1, that adds up to 2. And 3 does not divide 2. So 3 does not work. Let's see. 4 is that the last 2 digits have to be, the 4 must be able to divide the last 2 digits. That's not true. 4 doesn't divide 1. Okay. Let's see. 5, it has to be that it divides the last digit, but 5 does not divide 1. So 5 doesn't work. Let's see. And 6, I'm just going through the rules, by the way, guys. That's all that happens here. 6 has to, only divides the number if 2 divides it and 3 divides it. But we know that's not true, so 6 does not work. 7 is a weird rule, so I'm just going to look at it and try doing 7. Let's see, 7 goes in once. That's 7, 3, 0. So that's 4 to get me 28. Gets me 21. Let's see. 7 goes into 21 3 times. Is that right? Because that's not what your textbook has. Your textbook has a different number. 143 times 7. I'm just going to test it out. So it's 21. That's... Yeah, did I do something wrong? It's 28, 29, 30. That's 10. Yeah, that works. All right, so this 7 works, so this one is also a composite. Your textbook was talking about 11. Don't know why. It skipped over 7 for some reason. Okay, and then this last number, let's see. I have a product of odd numbers, so a bunch of odd numbers being multiplied. And there's actually a rule that you don't know at this point in time, and I don't expect you to memorize it either, but the product of odd numbers that multiplied is actually going to be odd. And you can consider why that works later. Should I show that to you guys? Let me see, how much time is in the video so far? Yeah, I think I have time to show you. I'll show you in just a second. So the product of odd numbers multiplies an odd number, and then we add one more to it. That makes this an even number, which means that 2 divides this number, which means that it is also composite. So that's interesting. All 4 of these examples, they're all composite. So let me explain that rule really quickly. The odd numbers multiplied gets you odd. Let me try and erase all this. Okay. So let's say I have an odd number. That's the format for it. And I multiply it by another odd number. I get 4nk plus, just multiplying it out, 2n plus 2k plus 1. Well, this is even, this is even, this is even. So when I add up all those even numbers, I'm going to get another even plus 1, which is an odd. So that's all that's happening here, just so you guys are aware. Let me pause the video real quick. Okay, so let's talk now about taking these primes and composites. Well, actually, let's take some composite numbers, and we want to find what we call our prime factorization. Can we take our composite number down to only prime numbers? And you guys have actually done this for a long time, so that shouldn't be, the answer to that question should not be a surprise to you. So let's go with the number that we were working with, 1564. And I know it divides by 2. I don't remember, I'm lazy, so I don't feel like doing it by hand. I don't expect you to do that by hand, because I know that we all know how to divide. But why waste your time when you're trying to apply your brain to something else? So I'm just going to keep dividing by 2 as long as I can. Whoops. I should have just clicked divided by 2. Gets me 391. Let's see. Is that divisible by 3? Let's see, 391 divide, let's see, that's 3 plus 9 plus 1, that's 12, 13. That doesn't work. So it's not divisible by 3, 4, 5, 6. Let's see, can I do it by 7? Let's see. Oh, you know what? I guess this is a good time to just show my online students how the 7 rule. It's weird. I told my in-person students, I do not expect you to memorize it. But anyway, so 391, what you do is you take the last number, you multiply it by 2, and you subtract it from the first number. So 39 minus 2, that gets me 37. 3 minus 2 times 7, that gets me negative 14. 3 minus 14 gets me negative 11. Well, that doesn't work either. So I don't believe that it is divisible by 39. Or divided by 7, sorry. Let me test it out. Divided by 7. Doesn't work. 391 divided by, well, 8's not going to work because it's not even. 9's not going to work because the sum is 13. 10 isn't going to work. Let's try 11. So it looks like it's not working, but unfortunately, prime numbers make this kind of difficult. So what might be helpful when we're finding this is to actually have our prime numbers available. So I'm just going to do a quick search real quick. Prime number list. Oh geez, this is a huge set here. And we will talk later um, about how to simplify this process, by the way. First of all, let me check, is 391 on this list? No, it's not. So it's not a prime number. Oh, no. So let's see. Let's actually set this one to the side for now. And we're going to talk about this. Can I select all of this and move it over? Whoops. Yeah. So we're going to talk about this later once we've talked about, I somehow erased some of this. Once we've talked about how to determine if a number is prime or not, which might actually be coming up soon. So let's work with a different number then. Let's work with, let's make it difficult for ourselves again. Let's go with 1001. We know that 7 works, although we don't know 7 and what. 143, which I don't know what that divides by. It may not divide by anything. It may be a prime number. Am I making things really hard for us? It's not a prime number. Okay, 143. Let's see. Let's divide that by 7 again. Let's try that. Nope. Let's divide that by 11. There we go. Yeah. I just took a random guess. Usually when you don't recognize a number, it helps to guess 7 and 11 because those are difficult. And so those are all prime numbers. I know that just by memory at this point. And so I now have my prime factorization. Notice that I crossed off the numbers that I broke down. I always do that. So that way I know the only numbers that remain are the ones that are not crossed off. And that's my prime factorization. Let's try a different one. Let's go with simpler this time now that we've done more difficult. I'm just going to break this down. And if you wanted to break this down on your own, I'm so sorry that I just jumped straight into it. That's not usually how I like to do things. I should have given you a little time to pause it and try it first. So anyway, 260 equals, I have 2 times 2 times 5 times 13. Notice the first thing I did. I wrote them out in order from least to greatest. And then the next thing I'm going to do is I'm actually going to write the powers. That 2 is going to be condensed. And this is the format that my math lab in your textbook expects. I'm a little less rigid, but I do want you to be as clear as possible. Now, note, I picked 26 and 10 for my first numbers. I could have picked different ones. I could have done like what I did before with the 1564 with 2 and 130, 2 and, what would that be? I don't even know. Oh, 65. And that would be a 5 and a 13. I cross off what I broke down, and notice we've still got the same numbers. No matter which 2 numbers you start off with, as long as you do it correctly, you will still get the same answer in the end. So that's just some prime factorization, and this leads us to a topic, or a theorem. It's called, which is kind of a heavy name for it, the fundamental theorem of arithmetic, which is what we're at right now. We're not at algebra or anything. And basically this states that, I'm going to pause it so that way you don't have to watch me write everything out. Alright, so your textbook has this written basically like this. Each composite number, so any number that is not prime, can be written as a product of primes in one way only. So it's not like you can have a bunch of different products and change them out. You can't have 2 squared times 5 times 13 and then say 260 is also 7 squared times 5 times 13. You can't change the numbers. It's just that you can change the order. You can write them out as... Did I turn off my pen? Yes, I did. You can write it out as 5 times 13 times 2 squared. I like to stick to least to greatest just so that your answer is the same as everyone else's, but that's not a big deal. Now, I don't know why your textbook tries to change from the factor tree. If you have trouble with this factor tree breakdown, let me know. Let me know that it causes problems for you, and I can talk to you about how you can use different formats, which is basically a T-chart. But I don't want you to worry too much about what else you see in your textbook. Let me erase all this real quick. It uses, oh, geez, this eraser is really difficult, really finicky. And try not to erase the other stuff that we need to come back to. Anyway, your textbook has something that says, you take 260 and you divide it by 2, you get 130. You divide it by, I think they put a 2 again, you get 65, 5, and 13. I don't know why they're trying to reinvent the wheel here, but they did try. Anyway, so you, actually let me pause it real quick. Let me come up with the next example. Okay, your textbook next talks about the topic number of whole number divisors, which basically means, so let's say 24. I go 1 and 24, 2 divisors, 2 and 12, 3 and 8, 4 and 6, and then I actually have all the possible pairs. So they will always come in pairs, even if one pair is, for let's say 25, 5 and 5. They always come in pairs. So anyway, the number of whole number divisors is simply how many of these we have. And I don't like the way that they do it. They have you write it out 1, 2, 3, 4, and then 6, 8, 12, 24. If this works for you, that's totally fine. But they do a little arc for 1 and 24, 2 and 12, 3 and 8, and 4 and 6. It can get confusing to me, but that is just because I never learned it this way. There's nothing wrong with learning it a different way than your teacher, though. So anyway, what I have done for a long time, is I will write the number and I'll start with 1, and I'll just go to the very next sets of numbers and make the pair. So 1 pair, 2 pair, 3 pair, 4 pair, and then I would write 5, well nothing works, and then I would write down 6, but 6 is already here, so I now have all the possible pairs, and I'm done. So the method that they use to find the number of whole number divisors is useful for a number like 391 or 1564 because you don't know how many more that you go on to, but it's not something that I expect you to know because it uses a little bit more calculations. So I just want you, if you want to know how to figure out theorem 4-13, which is so theorem 4-13, let me know. We can work on it together. We can discuss it, but otherwise don't focus on that part. All right, the next topic is how we're going to get the rest of this factor tree, and it simply says, if any number is prime, I'm sorry, if a number is not prime, if it's composite, then that number has at least one prime factor, because of course it's composite, and that has a prime factor p, and that has this formula for it. Sorry, that was my dog. She's over here just causing trouble. Anyway, so I need to know all of the prime numbers and their squares less than or equal to 391, because I want to continue breaking that number down. So I'm going to go back to my prime number list, and let me do some squares here. So let's see, 13 squared, that's 169. 17 squared, I don't remember what that is. Let me do it. And I'm just trying to show you guys that it doesn't hurt to just work it out again. 19 squared is 361. Wait, we were working with the number 391. Okay. Let's see. Let's go with 23 squared, that's 529. Okay, so I only need the numbers, the prime numbers, up to 19. So 2, 3, 5, 7, 11. Write those down. 2, 3, 5, 7, 11. 13 was next. Whoops. I think it's 17 is next. Yeah, 17 and 19. All right, these are all my possible prime numbers that break up or that are factors of 391. And I know 2 does not work. I tested 3. I know 5 does not work because it doesn't end in 5 or 0, meaning the last digit is not divisible by 5. I tried 7. I tried 11. So it's either 13, 17, or 19. So 391 divided by 13 doesn't work. 391 divided by 17, that works. There we go. So I can break this number down now into 17, and I think the other number was 23. So there's a lot of buildup for one more factor pair, but I wasn't able to figure it out before, and I wasn't going to try and do every single number, so I just used this rule. This rule narrowed it down to essentially 3 more numbers for me to try, rather than going 11, 12, 13, 14, 15, 16, and up to 17. So, cross off what has been broken down. 1564, its prime factorization is 2 times 2 times 17 times 13. Oh no, 23. Sorry. I'm going to rewrite that as 2 squared times 17 times 23. And that is my prime factorization. And you know what? I can actually test this out. Just make sure I did it correctly. So I can do 2, I should do squared, but I'm using my keyboard and it doesn't have an up arrow easily accessible. Times 17 times 23. 1564. Did it correctly. Looks good to me. So this is how you determine whether a number is prime or not. And your textbook, I don't like it because all it does is ask you to do more examples of this calculation. If I can think of any valuable ways for us to work through or to use this or to apply this rule, I will. But just so you're aware, I'm not going to do more examples of this right now. Okay, I'm going to give you a second to read through this problem that we have here. And I'm going to pause the video while you do that, and hopefully you pause your video as well. Okay, so hopefully you've already started breaking this down, and I would recommend that you give it a shot, try and set things up before I actually continue talking, so just pause the video. I'll give you like 2 seconds. Okay, now Monday, we know that they sold $1843 worth. And those dollars come from some number of bears, I'm sorry, the cost of each bear times some number. And then Tuesday, the same thing happened. 1957, though, is our new number. And the cost is still the same, but the number of bears is different. Well, it should be different if that's what's happening here. And so we want to know what is X and what is Y. We actually don't care about the cost, but it might be helpful because if we look at these numbers, we see that they both have the same factor, and the cost is a whole number. So if I can find a whole number that both of these values share, then that is the key to finding the rest of it. So let me break down each of these values. Let's see. So it's 9 plus 7, 16. That's not going to work. Yeah, and let's see. 2 doesn't work, 3 doesn't work, 4 doesn't work, 5, 6, 7. Does 7 work here? You know what? It might be more valuable for me to... No, so 7, 8... Just trying to break down this number right now. So 1843 divided by 7 doesn't work. 1843 divided by 8 doesn't work. I'm not going to do it like this. You know what? I think I have to. Because 8, 9, 10, Let's see, does 11 work? 1843 divided by 11. Let's see, 12. I don't think you guys need to know the rule for that one right now. Let's see, 13. That is a prime number, so I wouldn't have been able to test that before. 14. 15. And hopefully you'll notice that I'm just testing each number right now, only because it's a big hassle to do that rule from last time, the p squared is less than or equal to n, because n is huge. Okay, so let's go 1843 divided by 16, 1843 divided by 17, divided by 18, 1843 divided by 19. All right, I've got a whole number finally. So I've got 19 and 97. Let's see, 19 is prime. 97, I believe, is also prime. Let's see, yeah, it's prime too. So those are the only numbers I was going to be able to pick here. And then let's see, 1957. I'm going to have to spoil it a little bit for you guys because both of these numbers are prime too. So 19 and 103, but now you see how you would find these two numbers. And look, there's our cost right there. So that's C because they both share that. They both have C here, and they both have 19 here. That means that C equals 19, which means that X equals 97, and Y equals 103. That's how many bears they sold each day. This is an application problem that I think would be useful for you guys to understand and be sure that you can work through. And I don't know if people are doing this, but I would recommend just scanning through the assessments at the end of each section and seeing if there are any problems that you think might be a good challenge for you. That's where I source a lot of stuff from. Anyway, so this section, prime and composite numbers, we talk about quite a bit of individual topics related to these numbers. Something that my students in class did, let me clear this page real quick, and this will be the last topic from today's video, which is actually really short in comparison to the ones I've been making lately. I made one for my trig students today since I stayed home, and that one was an hour and 20 minutes. Anyway, so something that, oh, you know what, it's actually probably better if I just search it, that would be useful for my online students to do is called the sieve of Eratosthenes. And I just think, I'm sorry, hang on. Okay, sorry. So my in-class students, you can tune out at this point. We've already done this, but my online students, something that will help with divisibility and with primes and composites is what's called the sieve of Eratosthenes. And essentially, this Greek philosopher came up with a way to find the prime numbers without having them memorized. You just need to use divisibility and patterns. And so I have a link here that shows it pretty well. I did like the way we did it in person with my students because we use different colors for each different multiple, but it doesn't have to work out that way. And so if you like what you see here, it can actually just show things for you just fine. And it gives you tasks. It says your first task is click on 1, and you click all the multiples of 2 except for the number 2 itself. And you go on. I did it all just now, and honestly, it gets a little tiring. But it is pointing out to you all of the numbers that are composites. And so you continue working through it until each of the tasks has been completed. And you go up to number, I think it's 47 before it stops you. That's a little overkill. But either way, it does have you see a ton of different primes and their multiples and how those fit on this grid. And so I would recommend you work through this sieve. And just so you guys know, the term sieve is I think it's kind of like panhandle. You know, it's got a wire or plastic mesh held in a frame used for straining solids. So you're straining the composites out to leave behind the primes. Just kind of like when you're panning for gold. You take a bunch of dirt in and you have some water there and you just shake the dirt through the mesh until until all that's left behind are the gold flecks. So hang on just a second. Okay, well, I couldn't figure anything out. I was trying to find a nice little GIF and be cutesy and say, this is the gold that's in the mesh right here. Let me move my mouse. This is the gold right here, and those are the primes, and those are the composites falling through. But it doesn't really hold very well with flour and sifting. Anyway, so that's a little activity that I recommend you guys work through at this website here. Hopefully this video was helpful, and thank you guys for bearing with me with regards to not being able to go in person.